Interfering light waves. When two traveling waves interfere, the resultant amplitude of two superimposed waves is 2a cosine of 1/2 phi, where phi here is the phase angle between the two waves. But what we observe is the intensity. The intensity is the amplitude squared, which gives us 4a squared cosine squared of 1/2 phi. But the intensity of one of the waves is I naught, which is equal to a squared. And it is customary to talk about the relative intensity, which is written as Im over I naught is equal to 4 cosine squared of 1/2 phi. That's the relative intensity. For maximal interference, we had to differentiate between constructive and destructive interference. For maximal interference, we rely on phi equal to 2 pi divided by lambda dr to determine constructive and destructive interference. I could talk about constructive or destructive interference due to path difference. So if the path difference was an integral number of wavelengths, then we had constructive interference. If we had half odd wavelengths, then we had destructive interference for the path difference. Or we could talk in the language of the phase difference. If the phase between the two waves was a multiple of 2 pi, we always had constructive interference. If we had odd multiples of pi, then we always had destructive, where MC and MD stand for 0, 1, 2, 3, and all of the integers. But it is the relative intensity is what we measure. So the relative intensity, which is equal to 4 cosine squared of 1/2 phi, if it's constructive, then I relative is maximal. If it's destructive, then the relative intensity is 0. Applying these ideas to light, if I have two light waves that have a path difference, they acquire a phase difference. So therefore, the effective amplitude is 2e naught cosine of 1/2 phi. The intensity, which is the relative intensity then, if it's constructive, I'm going to get a bright spot. If it's destructive, I'm going to get a dark spot. Interference of light waves is about determining the cause of the phase difference between two interfering light waves. There are two possible situations we will encounter. Phase difference due to path difference. This is what we're going to spend most of our time on. Then there's going to be a phase difference due to reflection, as well as a path difference when we talk about thin films. Before we get started with phase difference due to path difference, we need to talk about what are monochromatic and coherent light sources. Interference effects are most easily observed when we combine waves of a single frequency. That is, monochromatic light is light of a single color or a single frequency. An example of a monochromatic light source is we could use the FET wave interference applet. So here's a light source that is emitting light, and what you're seeing here is that there's only one single frequency that this is occurring at. We could talk about this in terms of wavelength, but frequency is more fundamental than wavelength. This is a monochromatic source here. Another monochromatic source that's very common is a red laser. So this would be a monochromatic light source, one single color. However, most light sources are not monochromatic. Examples are light bulbs and flames. They emit a continuous distributions of many frequencies or many colors. Monochromatic sources are specialized sources, and the most common of these sources are lasers. So what does this all mean? Imagine that I have two light bulbs. One is light bulb 1, one is light bulb 2. They're both emitting two different types of colors of wavelengths. What you would find here is that no interference patterns will ever occur. No interference patterns will be observed. That is, no regions of constructive, bright regions, and destructive, dark regions will be observed. But frequency alone is not suffice to produce constructive and destructive regions in light. We also need coherent sources. When two light bulbs interfere, they do not produce a stable interference regions. Why is that? A classical picture has many atoms vibrating back and forth to produce light from a light bulb. A single atom in a light bulb emits about 10 to the 8 light waves per second. The problem is the waves change their phases too quickly and randomly that our eyes cannot detect this. Light waves that have different and changing phases is called incoherent light. Light from a light bulb is incoherent and will not form interference patterns. If interference is to continue occurring at some location, like we captured on a screen, the source of the waves must be coherent. This means the phase between the two sources is fixed and unchanging, such that the phase difference or the phase is a constant no matter what. Lasers are both monochromatic and coherent sources, and therefore these can be used to form an interference pattern on a screen. Two-slit interference. In 1801, Thomas Young performed his historic experiment that demonstrated that light was a wave. Young used monochromatic light that fell on two closely spaced narrow slits. So here are the two narrow slit openings, and then he shined light that was monochromatic onto these two slits. These two slits now acted as two coherent light sources. These interfering light sources then produce a series of alternating bright and dark fringes, or bright and dark spots. This could only be explained by wave interference. These series of bright and dark fringes can be completely described by their path differences and phases, where phi is equal to 2 pi divided by lambda delta r. To describe this pattern in detail, we must answer all of these characteristics. 1. The bright and dark fringe numbers, that is MC and MD. The location y of m, or the angular location theta of m of a particular fringe. 3. The total number of bright and dark fringes. The intensity IM, or I relative, of part of a fringe. Two-slit interference setup and explanation. So in red here, I have monochromatic light waves, and the spacing between these lines tells us the wavelength. So as this light impinges on this screen, there are two slits, slits number 1, slit number 2. What happens then is that these waves then become two coherent light sources, and then they spread out or fan out, and then they overlap at some point on the screen here, this viewing screen, where we then observe bright and dark, constructive, destructive spots or fringes. All interference spots or fringes can be explained by path differences of light waves, creating a phase between them according to delta r, the path difference between these two waves. If they're integer numbers of wavelengths, then it's constructive. If they're half integers of wavelengths, then it's destructive. MC and MD equal the same values, and it's 0, 1, 2, 3. Let's start with constructive interference. This is what we know. Delta R equal to 0 implies that both waves travel the same distances. This is our 0 point. We identify that by MC equal to 0. Delta R equal to 1 lambda. One wave travels farther by 1 lambda. This is what we call our first interference, and it's labeled by MC equal to 1. Delta R equal to 2 lambda. One wave travels farther by 2 lambda. This is our second interference. We label that by MC equal to 2. We now use an applet to explicitly show these path differences that I just explained. So here's an image of the applet. So I have two coherent sources. So that little red dot and that little red dot are sources 1 and 2. If you look at the image here, what you're finding here is that this region are regions of constructive interference. These blurred out regions are destructive interference. Once again, the regions where you see well-defined waves is constructive. The regions where you see blurred out regions, it's destructive. This means here, so when I look at constructive, what I see here is that I see bright, dark, bright, dark. What that means here is that these bright regions are the crests of the waves overlapping, producing a bright spot. This dark spot appears dark, but it's actually not. It's the troughs of the waves overlapping. So this literally means constructive interference. If you look at a region of destructive interference, you get this blurred out region. This implies that I have out of phase waves where I then have zero amplitude. So therefore, this is a dark region. Now let's go run the applet. This applet here now has two active sources that are producing waves. And what you're seeing here is that I get regions of constructive and destructive interference. Now the important thing here is that if I pick one region, you're going to see that I have two waves. And so what you're seeing here is that these two waves are traveling from point number 1 and point number 2. They're traveling the same distance. These waves have traveled a distance of 0 wavelengths and are in phase, therefore they produce constructive interference. So this one would be MC. So now if I go to the second one, bright spot, you're seeing that this second wave is traveling farther by what? 1 wavelength. And you could see that this is 1 wavelength difference than the other source here. As a consequence, you get constructive interference. If I go to the next region, which is right here, you could see here that what you're seeing, if I freeze the wave, the path difference of the second wave is 2 wavelengths difference. But when I do that, you could see here that I get constructive interference at that point. So now I've made 4 images of each of the situations. If I go to the first bright spot or constructive interference region, the path difference is 0. If I go to the second constructive interference region or bright spot, the path difference between these two is 1 lambda. Then I get 2 lambdas. Then I get 3 lambdas. So what I have here is I've now set up 4 setups to look at wave number 1, wave number 2 that are traveling these distances. Let's draw the first one. Wave number 1, wave number 2 travel the exact same distance. Therefore, delta R is equal to 0, and this is MC equal to 0. Let's go to the next one. When I draw the next time the waves constructively interfere, note that the green ray is traveled farther than the red wave. But by how much? If I draw a perpendicular line from the beginning of ray 1 to ray 2, such that this ray and that ray have the exact same distance, then this little tiny bit right here is the path difference between ray 1 and ray 2. In order to form constructive interference, length delta R must be lambda. Therefore, that first interference of constructive has to be MC equal to 1. Look at the third case, or the second case here. What you're seeing here is again ray 1 and ray 2. Those two lengths are congruent, but this distance here is now larger because it's higher up. It had to travel farther, so therefore delta R must be 2 lambda, which then means that MC must be 2 as well. And following the last one, we could see here that in order for these guys to have constructive interference, the path difference has to be 3 lambda. Therefore, MC equals to 3. Now I want to repeat the same thing for destructive interference. So for each of the 3 cases here, I have ray 1 and ray 2, and as I go higher up the screen, I'm going to get a bigger path difference between the two. But the big difference is, if you look at this image here, I'm half a wave difference in my path difference. In other words, the destructive interference that I'm seeing on the screen here has a path difference of half a wavelength, and that's what we call MD equal to 0. That's the first time that we could get destructive interference. So if I look at this guy over here, you could see that the path difference is 1.5 waves. So therefore, I have to write 3/2 lambda for the path difference. And that's what we call MD equal to 1. And if you look at the third situation over here, you could see that it's not 1.5 waves, it's actually 2.5 waves, which we write as 5/2 lambda. And this is MD equal to 2. Putting this all together, we want to represent two-slit interference on a screen. So I have this monochromatic coherent waves that are going to be coming out of these 2 sources. On a screen, I get a series of bright spots, which are represented by the red, and dark spots, which are represented by the black. So I get a sequence of these interference patterns that occur. So the central line defines MC equals to 0. And then as I go up, I'm going to define that to be the first bright fringe, MC equal to 1, the second bright fringe, MC equal to 2, and then MC equal to 3. Now, since this is upwards, downwards, instead of labeling it 1, I'm going to label it -1. So if I have MC -1, then it's on the bottom. And then I get MC -2, -3. The path difference for each of these bright fringes then is given by the central one being no path difference. The first fringes have a path difference of lambda. The second bright fringes have a path difference of 2 lambda. The third bright fringe has a path difference of 3 lambda. Focusing on destructive interference, it is very common for textbooks to label MC and MD just by M. But there is a difference between these 2 numbers. So if I look at dark fringes, note that there are 2 0 points, whereas in constructive there's only 1 0 point. So the first dark fringe occurs at MD equal to 0, and then the second one is MD equal to 1, and the third one is MD equal to 2. Then of course there's the symmetry from the central line. Each of these path differences then have to do with odd half wave multiples. So in this 0 case, it's half a wave. For 1s, it's 3 lambda over 2. For 2, I'm getting 5 lambda over 2.